Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The human body that carries you through your daily life is the product of roughly 300,000 years of evolution, a biological masterpiece that emerged from the savannas of Africa. But what will our species look like after another 1,000 years of existence? This isn't mere speculation, but an exploration grounded in our understanding of evolutionary biology, genetic engineering, and the mounting pressures of our changing planet. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Evolution has traditionally operated through natural selection, a painstakingly slow process of random mutations creating variations, with environmental pressures determining which traits persist. Under natural circumstances, 1,000 years represents merely 40 generations of humans, not nearly enough time for significant evolutionary changes. However, our species has fundamentally altered this equation. The development of agriculture approximately 12,000 years ago marked humanity's first major divergence from our evolutionary trajectory. Genetic studies reveal that this shift triggered numerous adaptations. Lactose tolerance emerged in dairy farming populations, while communities cultivating starchy grains developed additional copies of the amylase gene to better digest carbohydrates. These changes occurred relatively rapidly because they offered immediate survival advantages. Today, we face an unprecedented situation. Modern medicine has largely neutralized many selective pressures that once drove human evolution. Genetics. Conditions that would have been fatal before reproduction can now be managed throughout a full lifespan. Concurrently, our technological capabilities have introduced new evolutionary forces, from industrial pollutants to electromagnetic radiation to processed food diets. The most dramatic shift, however, comes from our growing mastery of the human genome itself. CRISPR-Cas9 and related gene editing technologies already allow scientists to precisely modify genetic material. Early applications focus on eliminating hereditary diseases like Huntington's, cystic fibrosis, and sickle cell anemia, which affect millions worldwide. As these technologies mature over coming decades, they promise to fundamentally alter our relationship with our own biology. Genome sequencing costs have fallen from $3 billion for the first human genome in 2003 to less than $100 today. This exponential improvement suggests that comprehensive genetic information will be standard in healthcare within a generation. When combined with increasingly sophisticated editing tools, humanity stands at a crossroads unlike any in our evolutionary history. Climate change represents another profound pressure on our species. Rising global temperatures, shifting precipitation patterns, and increasing extreme weather events will reshape human habitats worldwide. While technology may mitigate some effects, our bodies will face challenges ranging from heat stress to new disease vectors to altered nutrition profiles in food crops. What makes our species unique is our capacity to anticipate and deliberately respond to these pressures. Rather than waiting for natural selection's blind process, we now possess tools to direct our evolutionary future intentionally. This represents both unprecedented opportunity and profound ethical questions that coming generations must navigate. As we peer into humanity's potential biological future, we must consider two parallel tracks: the continuing subtle influence of natural evolution shaped by our modern environment, and the potentially dramatic impact of technologies that allow direct intervention in our genetic code. This tension will define what it means to be human in the millennium ahead. The single greatest force reshaping humanity's biological future will likely be the continued advancement of genetic engineering technologies. By 2100, somatic gene therapies, genetic modifications that affect an individual but aren't passed to offspring, will likely be routine medical procedures, as commonplace as vaccinations are today. These interventions will target everything from cancer susceptibility to neurodegenerative conditions, potentially extending healthy lifespans well beyond 100 years. More controversial will be germline modifications, genetic changes that affect not just an individual, but all their future descendants. Many countries currently prohibit such interventions, but regulatory frameworks will inevitably evolve as technologies improve and competitive pressures build between nations with different ethical stances. The first widespread germline modifications will likely target clear genetic disorders, eliminating conditions like Tay-Sachs disease and cystic fibrosis from family lineages permanently. As safety improves, the definition of therapeutic may gradually expand. Modifications to reduce susceptibility to heart disease, diabetes, or Alzheimer's could benefit billions and dramatically reshape healthcare economics. By 2200, enhancements targeting improved immune function, cellular repair mechanisms, and metabolic efficiency may become increasingly common, creating a biologically distinct cohort of humans with significantly enhanced disease resistance. The potential for cognitive enhancement presents even more profound implications. Several hundred genetic variants associated with intelligence have already been identified, though each exerts only a tiny influence individually. As computational genomics advances, scientists will develop more sophisticated understanding of how these genes interact. Initially, genetic screening may identify embryos with naturally favorable combinations, but eventually, precise modifications could potentially enhance neural development, synapse formation, and neurochemical signaling pathways. Importantly, access to these technologies will not be universal. Economic disparities, regulatory differences between nations, and cultural attitudes toward genetic modification could create unprecedented biological stratification of our species. Some communities may reject all genetic interventions on religious or philosophical grounds, while others embrace them enthusiastically, potentially accelerating divergence within humanity. By 2500, these diverging paths may create distinct human subpopulations with significantly different capabilities, disease susceptibilities, and lifespans. This wouldn't represent speciation in the traditional sense. These groups would remain interfertile. But biological differences might exceed those between the most divergent human populations today. Meanwhile, genetic adaptation to changing environmental conditions will become increasingly deliberate. As climate zones shift, engineered tolerance to heat, drought, or new disease vectors may become essential for populations in vulnerable regions. Humans inhabiting extreme environments, whether polar research stations, desert settlements, or early extraterrestrial colonies, might receive specialized genetic packages optimizing their bodies for these challenges. Beyond genetic engineering, integration with technology will reshape human capability. Neural interfaces connecting brains directly to computing systems are already in early development at companies like Neuralink. Initially aimed at treating conditions like paralysis or blindness, these technologies will eventually enhance cognitive processing, memory storage, and direct brain-to-brain communication. By 2300, the distinction between biological cognition and technological augmentation may become increasingly blurred. Perhaps most profound will be the eventual ability to dramatically slow or even reverse biological aging. Several promising pathways already show potential: telomere preservation, senescent cell removal, mitochondrial optimization, and epigenetic reprogramming. Within 300 years, these approaches may converge into comprehensive age management systems, fundamentally altering humanity's relationship with mortality itself. These innovations won't spread evenly across human populations. Geographic, economic, cultural, and philosophical divisions will create a complex mosaic of biological futures. The resulting divergence may represent the most significant branch point in human evolution since our ancestors left Africa roughly 70,000 years ago. No species exists in isolation from its environment, and humanity's future form will be profoundly shaped by the rapidly changing planet we inhabit. By the year 3000, Earth's climate will have undergone dramatic transformation. Even Under optimistic scenarios where humanity successfully transitions to sustainable energy systems and stabilizes atmospheric carbon dioxide levels, significant warming and its cascading effects will have reshaped human habitats worldwide. Rising. Sea levels will have inundated coastal regions that once housed billions of people, forcing massive migration to higher elevations. Heat stress will render substantial portions of the tropics and subtropics periodically uninhabitable without technological protection, while formerly temperate regions experience increasingly frequent extreme weather events. These pressures will drive both technological and potentially biological adaptations. The first adaptive responses will be behavioral and cultural. Heat-adapted work schedules, architectural innovations, and clothing technologies will help humans cope with changing conditions. However, genetic adaptations may eventually follow. Natural selection already favors different body types in different climates. The tall, slender builds prevalent in traditionally hot regions maximize surface area for heat dissipation, while stockier frames in colder regions conserve heat more efficiently. In a warming world, selection pressures may subtly shift human morphology toward heat-adapted body types. More sophisticated adaptations might emerge through deliberate genetic intervention. Enhanced melanin production could protect against increased ultraviolet radiation, while modified sweat gland distribution and function could improve cooling efficiency. More speculative modifications might include optimized hemoglobin variants to maintain oxygen transfer efficiency at higher ambient temperatures or enhanced kidney function to conserve water in drier regions. Disease vectors represent another critical environmental pressure. As warming temperatures allow mosquitoes, ticks, and other disease carriers to expand their ranges, humans will face exposure to pathogens their ancestors rarely encountered. Genetic variants conferring resistance to these diseases may be selected for naturally, but engineered immunity could accelerate this process dramatically. By 2500, customized immune system modifications based on regional disease profiles might become standard preventative health care. The microbiome, the ecosystem of trillions of bacteria, viruses, and fungi that inhabit the human body, will represent another frontier of adaptation. Recent research indicates these organisms profoundly influence everything from digestion to immune function to neurotransmitter production. As environmental conditions change and human diets shift in response to agricultural challenges, researchers will likely develop customized microbiome modifications to optimize health under new conditions. Atmospheric changes may drive respiratory adaptations. While technology will filter most pollutants, genetic modifications enhancing lung capacity or improving the efficiency of oxygen transport could benefit populations in regions with compromised air quality. Similarly, as ocean acidification and changing climate patterns alter marine food webs, humans may need to adapt to different nutritional profiles in available foods. Perhaps most significant will be modifications addressing the psychological challenges of an altered world. Humans evolved in natural environments with consistent cycles of light, seasons, and ecological relationships. As artificial environments become increasingly dominant and natural systems transform, neurocognitive adaptations, whether through training, pharmaceutical intervention, or eventually genetic modification, may help future generations maintain psychological well-being under conditions quite different from those that shaped our brains. By 3000 CE, humans living in different regions may exhibit significantly different adaptations to their local environments. These differences won't constitute speciation, but regional variants of humanity may emerge with distinctive characteristics suited to their specific environmental challenges. From high-altitude adaptations in mountain refuges to heat tolerance in formerly temperate zones to specialized adaptations for the artificial environments of megacities or extraterrestrial settlements. This environmental reshaping of humanity will occur alongside deliberate enhancements, creating complex interactions between natural selection pressures and engineered solutions, a coevolution of humans with both their changing planet and their own technology. Humanity's expansion beyond Earth will represent perhaps the most dramatic evolutionary catalyst in our species' history. By the year 3000, substantial human populations will likely exist throughout the solar system, from orbital habitats to permanent settlements on the Moon, Mars, and possibly the moons of Jupiter and Saturn. These environments present challenges fundamentally different from anything encountered during our evolutionary history. Reduced gravity represents one of the most significant biological challenges of space habitation. We've already observed concerning effects from relatively brief orbital missions, muscle atrophy, bone density loss, cardiovascular deconditioning, and fluid redistribution causing vision problems. Long-term settlers in low-gravity environments will face these issues throughout their lifespans, potentially leading to significant adaptations. Initially, technological countermeasures will predominate, centrifugal habitats generating artificial gravity, specialized exercise regimes, and pharmaceutical interventions. However, as permanent off-Earth populations grow, genetic engineering could offer more comprehensive solutions. Modified musculoskeletal development to maintain strength in reduced gravity, cardiac adaptations to maintain efficient circulation, and altered calcium metabolism to preserve bone density. Radiation exposure presents another critical challenge. Beyond Earth's protective magnetosphere, cosmic radiation levels increase dramatically. Early settlements will rely on shielding technologies, but long-term adaptation might include enhanced cellular repair mechanisms, improved radiation resistance in stem cell populations, and more efficient antioxidant systems to manage radiation-induced free radicals. Different gravity environments might eventually produce strikingly different human morphologies. Children born and raised in the Moon's 1/6 Earth gravity, or Mars' 1/3 gravity, might naturally develop taller, more slender frames with less dense bones, adaptations that would prove catastrophic if they attempted to return to Earth. Within 500 years of sustained off-world settlement, gravity-adapted subpopulations might become effectively unable to travel between worlds without extensive medical intervention. Atmospheric variations will drive further adaptations. Early Mars settlements will maintain Earth-like atmospheric pressure and composition within habitats, but atmospheric engineering of Mars, if attempted, would likely produce a thinner atmosphere with different gas concentrations than Earth's. Humans adapted for this environment might develop increased lung capacity, altered hemoglobin with higher oxygen affinity, and modified respiratory regulation. The confined artificial environments of space settlements will reshape human microbiology. Strictly controlled microbial ecosystems might reduce infectious disease, but could potentially lead to weakened immune responses to novel pathogens. Genetic engineering might enhance innate immunity to compensate, while carefully designed probiotic regimens would maintain essential microbiome functions. Psychological adaptations may prove equally important. Humans evolved in environments with natural light cycles, open horizons, and complex sensory stimulation. Space habitats will initially lack these features, potentially causing psychological stress. Future space-adapted humans might exhibit altered circadian rhythms, different stress responses, and modified sensory processing optimized for enclosed environments. By 2700, specialized human populations adapted to different off-Earth environments might diverge significantly from their terrestrial counterparts. Over generations, this divergence could potentially approach speciation, especially if genetic modifications become extensive enough to affect reproductive compatibility with unmodified humans. These diverging populations will face ethical and philosophical questions unprecedented in human history. What degree of biological modification remains human? Should adaptations be limited to ensure cross-compatibility between populations? As different environmental pressures shape different human communities across the solar system, our definition of humanity itself may require expansion. Additionally, the technologies developed for space adaptation may feed back to Earth, offering solutions for adapting to changing terrestrial environments. Techniques developed to enhance radiation resistance for Martian settlers could protect Earth populations exposed to increased ultraviolet radiation while water conservation adaptations designed for space habitats might benefit communities in increasingly arid regions of Earth. In this way, humanity's expansion beyond our home planet may ultimately enhance our species' resilience through biological diversification, creating not a single path forward for human evolution, but many parallel trajectories suited to the remarkable variety of environments our descendants will inhabit. Perhaps no aspect of future human evolution will prove more consequential than changes to our cognitive architecture. The human brain, a remarkable product of natural selection containing roughly 86 billion neurons and 100 trillion synapses, has remained fundamentally unchanged in structure since Homo sapiens emerged. By the year 3000, this may no longer be the case. The integration of neural interface technologies with human biology will likely progress through several phases. Early interfaces, already in development, focus on medical applications, restoring movement to paralyzed limbs or vision to the blind. Within a century, more sophisticated bidirectional interfaces will enable direct human-computer interaction, allowing users to access information networks through thought alone. By 2300, these technologies may evolve into fully integrated brain-computer interfaces, creating hybrid cognitive systems where biological and digital processing occur seamlessly. This would represent not merely a tool used by the brain, but an expansion of the brain itself, extending human cognitive capabilities in ways difficult to imagine with our current mental architecture. Memory enhancement represents one obvious application. The biological mechanisms of memory, protein synthesis at synapses, neural network formation, and consolidation during sleep, have inherent limitations in capacity and reliability. Neural interfaces might offer perfect recall, potentially storing lifetimes of experience with digital fidelity, while maintaining the emotional and contextual elements that give memories meaning. Cognitive processing capabilities might similarly expand. Complex mathematical calculations, sophisticated simulations, and massive data analysis could become as natural as visual processing is for current humans. Creative cognition might be enhanced through systematic exploration of conceptual spaces, beyond what the unaugmented imagination could generate. Perhaps most profound would be modifications enabling new forms of consciousness. Enhanced sensory processing might allow perception of currently inaccessible aspects of reality, from ultraviolet or infrared vision to direct perception of electromagnetic fields. Modified temporal perception could allow subjective time dilation during critical activities. Even the fundamental structure of consciousness, the integrated experience of being, might eventually be subject to deliberate modification. Beyond individual enhancement, neural interfaces could enable unprecedented forms of human connection. Direct brain-to-brain communication might allow sharing of thoughts, emotions, and experiences with a fidelity impossible through language alone. Collective intelligence systems could emerge, where groups of enhanced humans collaborate with an intimacy and efficiency that redefines our understanding of social cognition. The integration of artificial intelligence with enhanced human cognition presents even more transformative possibilities. Rather than competing with AI systems, future humans might incorporate aspects of machine intelligence directly into their cognitive processes, adopting capabilities like parallel processing, perfect logical consistency, and specialized computational modules, while retaining the emotional intelligence, creativity, and meaning-making capabilities that characterize human cognition. These cognitive transformations would fundamentally alter humanity's relationship with knowledge and creativity. When any information can be accessed instantly through neural interfaces, education would shift from memorization to synthesis and application. Creativity might flourish as cognitive constraints are removed, potentially unleashing intellectual and artistic achievements beyond anything possible for unenhanced minds. However, cognitive enhancement also presents profound risks. Privacy would require radical redefinition in a world where thoughts might be directly accessible. Social stratification. could increase dramatically if cognitive enhancements aren't universally available. Most fundamentally, enhancing certain cognitive capabilities might inadvertently diminish others, potentially sacrificing aspects of human experience and understanding that prove incompatible with engineered cognition. By the year 3000, these cognitive transformations may have progressed to the point where enhanced humans possess mental capabilities as far beyond current humans as ours are beyond our primate relatives. This cognitive distance might create communication challenges between enhanced and unenhanced populations, similar to those we would face attempting to explain abstract mathematics to non-human primates. The philosophical implications are equally profound. If consciousness can be technologically modified, expanded, or transferred, what constitutes personal identity? If cognition spans biological and technological substrates, where does the self begin and end? The answers developed by our cognitively transformed descendants may require conceptual frameworks beyond those available to current human understanding. Human evolution doesn't occur solely at the individual level. We are fundamentally a social species, and the structures of our communities shape our development as profoundly as our biology. Over the next 1,000 years, social evolution may prove as transformative as genetic engineering or neural enhancement. Communication technologies have already radically altered human social dynamics. From writing to printing to telecommunications to the internet, each advance has restructured how humans connect, collaborate, and conflict. By the year 3000, communication technologies may have progressed to allow direct thought transmission, enabling forms of human connection previously impossible. Brain-to-brain interfaces will likely develop from crude beginnings, perhaps sharing simple sensory impressions or emotional states, to increasingly sophisticated systems capable of transmitting complex concepts directly between minds. The implications for human relationships would be profound, potentially enabling empathic connections of unprecedented depth and authenticity. Language itself, historically limited by the bandwidth of speech and the imprecision of words, may evolve into hybrid systems, incorporating direct concept transfer alongside traditional communication. Specialized thought languages might develop, optimized for sharing particular types of mental content, from mathematical reasoning to emotional experiences to aesthetic appreciation, with greater fidelity than possible through words alone. These communication advances would enable new forms of collective intelligence. Modern research already demonstrates that properly structured groups can solve problems more effectively than even their most brilliant individual members. Future social technologies might systematically enhance this collective capability, creating integrated cognitive systems where dozens, hundreds, or thousands of enhanced minds collaborate with an intimacy and efficiency impossible for contemporary humans. Decision-making structures would necessarily evolve in response. Current governance systems, from representative democracy to authoritarian control, all face fundamental limitations in information processing capacity and coordination efficiency. Direct democracy systems, enhanced by collective intelligence, technologies might enable hundreds of millions of citizens to collaboratively develop and evaluate complex policies with sophisticated understanding of their implications. Social trust mechanisms would similarly transform. Current institutions rely heavily on externalized trust, laws, contracts, and verification systems that compensate for limited ability to directly assess others' intentions. Enhanced communication might enable internalized trust based on transparent understanding of others' mental states, potentially restructuring everything from economic exchange to community governance. These developments would reshape the fundamental nature of human identity. While current humans primarily experience themselves as discrete individuals, future humans might routinely experience various degrees of cognitive merging during collaborative activities, temporarily forming composite consciousness systems before returning to individual identity. The psychological boundaries between self and other could become more permeable and contextual than the rigid separations we currently experience. Cultural evolution would accelerate dramatically. Ideas, techniques, and perspectives could spread with unprecedented speed and fidelity through enhanced communication networks. Cultural innovation might follow computational principles, with systematic exploration of conceptual spaces and rapid testing of novel social configurations. The rate of cultural change, already challenging for contemporary humans, might accelerate beyond what unenhanced minds could assimilate. These social transformations would create powerful selection pressures on human psychology. Traits that enhance functioning in highly interconnected environments, cognitive flexibility, emotional regulation, collaborative orientation, would likely be increasingly advantageous. Either through natural selection or deliberate enhancement, future humans might evolve increasingly sophisticated social cognition adapted to their hyper-connected reality. However, these developments also present profound risks. Privacy would require fundamental reconceptualization in environments where thoughts might be directly accessible. Power imbalances could be magnified if some groups gained privileged access to collective intelligence technologies. Most fundamentally, the human need for individual identity and agency might conflict with increasingly collective cognitive systems. By the year 3000, human society might function as a complex hybrid of individual and collective intelligence, neither the separate consciousness of current humanity, nor a homogeneous hive mind, but a dynamic layered system where individuals participate in various levels of cognitive merging according to context and preference. Understanding such a society from our current perspective is necessarily limited, as it would represent a form of social organization with no precedent in human history. The ultimate expression of this social evolution might be what some futurists term the global brain, an integrated planetary intelligence emerging from the network of enhanced human minds, artificial intelligence systems, and ubiquitous computing infrastructure. Whether this represents humanity's transcendence or the subsumption of human uniqueness remains perhaps the most profound question our species will face in the millennium ahead. As we've explored potential trajectories for human evolution over the next 1,000 years, one theme becomes increasingly apparent. There likely won't be a single human future, but many parallel paths reflecting different biological, cognitive, environmental, and social adaptations. By the year 3000, humanity may encompass greater diversity than at any point in our evolutionary history. This divergence begins with choice. As genetic engineering, neural enhancement, and other transformative technologies mature, different human communities will make different decisions about their implementation. Some groups will embrace radical enhancement, seeking to expand human capabilities in every dimension possible. Others will adopt more conservative approaches, accepting some modifications while rejecting others based on religious, philosophical, or cultural values. Still others may reject enhancement entirely, choosing to remain genetically and cognitively similar to humans today. Environmental pressures will further drive diversification. Humans adapted for life on Mars will necessarily develop different characteristics than those living in oceanic habitats on Earth or orbital settlements near Saturn. These adaptations, whether engineered deliberately or emerging through natural selection, will create distinct human subpopulations specialized for their particular environments. This biological and cognitive diversification raises profound questions about human identity and community. At what point do enhanced humans become something other than human? If populations diverge significantly, how will they maintain mutual understanding and moral concern? These questions have no simple answers, but how our descendants address them will shape whether divergence leads to conflict or complementary coexistence. Some futurists envision extreme scenarios where human descendants diverge into separate species unable to interbreed. While possible given enough time and separation, the 1,000-year time frame we've explored would likely produce significant diversity within a single species rather than speciation in the biological sense. The more immediate challenge will be maintaining social cohesion and ethical frameworks that encompass increasingly diverse expressions of humanity. This diversity may ultimately prove humanity's greatest strength. Evolutionary biology teaches that diverse populations are more resilient to environmental changes and challenges. By developing multiple distinct paths forward, humanity creates a form of evolutionary hedging. If any particular adaptation proves maladaptive, as conditions change, alternatives exist. This principle applies whether the challenges are environmental, technological, or social. Throughout this exploration, we've focused primarily on technological possibilities and their implications. However, the wisdom to guide these powerful capabilities remains humanity's greatest challenge. The coming millennium will test not just our scientific ingenuity, but our moral imagination, our ability to envision and create social structures, ethical frameworks, and governance systems that can channel these unprecedented powers toward flourishing rather than destruction. What seems increasingly certain is that current humans stand at an inflection point unlike any in our evolutionary history. For hundreds of thousands of years, our species changed through the blind mechanisms of natural selection, responding to environmental pressures we could neither predict nor control. Now we rapidly approach the ability to direct our own evolution deliberately, to shape not just our environment, but our very beings according to our values and vision. This transition from evolution by natural selection to conscious self-modification represents perhaps the most profound threshold our species has ever crossed. The humans of the year 3000 may look back on our era as we view the emergence of the first stone tools, a critical turning point when a species gained the ability to reshape itself as well as its surroundings. Whether this power leads to divergence, conflict, and potentially even extinction, or to a flourishing plurality of human futures exploring different modes of being while maintaining connection and common purpose, will depend less on the technologies themselves than on the wisdom with which we deploy them. The story of humanity's next 1,000 years remains unwritten, its pages awaiting the choices of generations yet unborn. Perhaps the most profound insight from this exploration is also the most humbling. Despite our best predictions and scientific understanding, the actual trajectory of human evolution will likely surprise us in countless ways. The complex interplay of biological, technological, environmental, and social factors creates a future resistant to simple prediction. What seems certain is that our descendants, whatever form they take, will face challenges and possibilities. We can scarcely imagine continuing humanity's ancient journey of adaptation, discovery, and transformation across the stars,